The climate control system using ESP8266 and Arduino IoT Cloud. Introduction. Temperature and humidity are critical parameters for many modern industries because of their long-term destructive effects on materials, equipment, and people. Special requirements for temperature and air humidity are relevant for the storage of medical and food products. Control of storage, temperature, and air humidity is important for various technological processes. One of the important tasks is to monitor the temperature and humidity of the environment without restricting the movement of the user. To ensure comfortable working conditions in the cold period, a system is needed that would allow assessing the state of temperature and humidity in premises for archival storage of documents, educational institutions, pharmacies, museums, libraries, offices, and warehouse premises. This will make it possible to efficiently use financial resources, and upon the improvement of the system, to automatically set the temperature on the premises during working or non-working hours and monitor the state of emergency. System architecture. The climate monitoring system is a software-hardware module for the wireless control using a Wi-Fi channel, which is integrated into the Internet of Things system and allows you to measure the temperature and humidity in the room and transmit the measured values via the Wi-Fi network with remote access from a cell phone, tablet, or personal computer, and performs remote control of an electrical appliance, air conditioner, or heater in manual or automatic control mode, depending on the given cooling heating algorithm. The climate monitoring system consists of a temperature and humidity sensor DHT11 and control unit with Wi-Fi network support, ESP8266 microcontroller, and executive device, relay module, power supply unit. Figure 1. Structure diagram of the climate monitoring system. The key component of the monitoring system is combined temperature and humidity sensor DHT11, DHT22, HDC1080, or BME280. The DHT11 sensor is a digital temperature and humidity sensor. It consists of a capacitive humidity sensor and thermistor. Also, the sensor contains an ADC for converting analog values of humidity and temperature. DHT11 outputs a calibrated digital signal. The minimum interval for reading data from the sensor should be 2 seconds. With frequent access, the measurement error increases. Software. Arduino IoT Cloud, an IoT platform used to buy supplies and manufacturers of smart devices to equip their products with functions of remote control, real-time monitoring, setting up alerts and notifications, and integration with smartphones and other devices. Arduino IoT Cloud data storage greatly simplifies data storage and provides a full range of services within the concept of the Internet of Things (IoT). It includes hardware and software, cloud services, and a knowledge base. To work with Arduino IoT Cloud 8.10, you must create and log into an account and add a new device to it, namely the NodeMCU ESP8266. To do this, go to the Devices tab and click Add Device. Figure 3. Editing a device to the project. Figure 4. NodeMCU ESP8266 port selection tab. The next step is to create a subject Things. To do this, go to the Things tab and click on Create. On the Things tab, there are 3 options need to be configured: variables, devices, and networks. To add variables that will be used in the program code, press the Add Variable button. The next step is to create a dashboard. To do this, go to the Dashboard tab and click Create. Figure 5. Project Dashboard Settings. Figure 6. Chart Widget Settings. After configuring the Arduino IoT Cloud platform, it's necessary to program the NodeMCU ESP8266 board to read data from the DHT11 sensor, transmit it to the cloud, and perform remote control functions. When adding variables to things, the sketch in the cloud is automatically updated. Most of the application code sketch is automatically generated by the platform. It's necessary to add lines to work with the DHT11 sensor and implement the remote control algorithm. To do this, open the Arduino Cloud Editor, Code Editor on the Sketch tab. As you can see, Figure 7. Editing sketch code automatically generated by the Arduino IoT Cloud platform. We physically connected the NodeMCU model with the connected DHT11 sensor and led simulating the operation of the relay to the computer. Figure 8 shows that the NodeMCU model is connected to COM9 and you can start verifying the project. If there are no errors, select the load button and download sketch to the NodeMCU model. Open the serial monitor module Figure 9 and observe the temperature and humidity data measured by the sensor and transmitted by the module to the computer through the virtual serial port. Results: the climate monitoring system is based on the ESP8266 microcontroller, which is part of the NodeMCU or Wemos D1 mini platform. The microcontroller organizes data transfer via Wi-Fi to an Arduino IoT Cloud platform. A DHT11 Senior was used as a combined temperature and humidity sensor. The GPIO2 port is used to control the executive device in a manual or automatic control mode depending on the given cooling heating algorithm. The experimental sample is implemented on the Node MCU model as an indication of the remote control mode. A blue LED built into the board used, which is connected by the catch code to the GPIO2 port, figure 10, an experimental sample of the climate control system based on the Node MCU module. Results: the online monitoring controller and control panel that was created on the Arduino IoT Cloud platform is shown in Figure 11. For the convenience of working with the Arduino IoT Cloud dashboard, you can install the IoT Remote mobile application on your phone from the official Google Play or App Store. The dashboard of the climate monitoring system used Arduino IoT Cloud. Conclusion: this article offers the practical aspects of implementing a climate control system based on the IoT module Node MCU wemos, a combined sensor DHT11 and a relay module with minimal cost and the possibility of adaptation to the monitoring and control system of premises of an educational institution. Current climate data are available online. The operator who directly controls the site sees all the information in real time or digital panel. This in turn allows for efficient use of financial resources, and upon the improvement of this system, to automatically set the temperature on the premises during working or non-working hours and monitor the state of emergency.